Okay. Okay, what do you see up here that reminds you of derivatives, Becca? Differentials, that's good, because that's related to the word differentiable, right? And what was your thought, Mackie? Lines. I like that you said lines. One would hope everyone would be saying lines. Why? Okay, let's talk about your ability to break a word down. All right? I know from experience, not so much. Okay, let's pretend the isation wasn't there. What would that mean? Linear, which means line. Okay, lines. Do what? Lines. Okay. How about the isation? Okay, so what's modernization? Making something modern. So
linear. Making something.
There we go. So Clark's like, couldn't answer any of the other questions, but I can put these pieces together. Making something a line. Okay. All right. Do you remember? I think we did this, and if we didn't, I will probably have to pause my video to get this to work. But when we zoomed in on the sine function, what happened? That's right. Looks like a line, right? If you take any function, let's rewind. When you're in science, how much have y'all played with microscopes? Not much. That's unfortunate. When you get to college, you'll get to see some amazing microscopes because you will see things that you can't imagine exist through the scope of a microscope. It's insane. All right, so anything that we zoomed in on far enough, no matter how curvy it was, would look straight. Kind of like that sine function. Now, on the sine function, it's a little more believable, isn't it? Because there's a lot of parts in there where it almost looks linear anyway, just looking at it. But anything can be. So that relates to our first term, locally linear. And we want to put beside that word, not necessarily a definition, but just a connection to make there, any differentiable function. Let me fix that E. That does not look like an E. Oh my gosh, I thought I had this back on the pen. Sorry. Undo that. Any differentiable function. What is a differentiable function? That's right. A function that has a derivative everywhere, right? Okay, well, let's just say I'm talking about, and this is an extreme case, by the way. Let's just say we're talking about an absolute value graph. Is it a differentiable function? Why? Because it has a corner. So it's differentiable everywhere but at its vertex, right? Okay, so obviously it would be locally linear everywhere but there just because of its shape, right? So any function that has a point at which it's not differentiable or some part that's not differentiable, then those functions are going to be not necessarily linear everywhere or locally linear everywhere. They're only going to be locally linear where the derivative exists. Does that make sense? Okay. All right. So I always debate about which way to do this. We're going to define the first word beyond what we've already talked about it. Now here's what's going to happen. This lesson is really easy, and I've told y'all this a lot of times, but you know how when something's really easy, when you first do it, it's probably the thing you're going to have the hardest time remembering? Because it doesn't really have an impact on you. This is going to be sort of that same sort of thing. I've had students during the AP prep window of time in this class say to me, what does locally linear have to do with anything? What's linearization? What are they talking about? And I'm just like, what? So just kind of remember that it's largely things you already know that you don't think you know. So if f is differentiable at a, and again, what does that mean? The function is differentiable. What does differentiable mean? It has a derivative. And that's important because of the fact that we can do, if we find our f prime, how would I figure out where it's not differentiable? If it's undefined. If the derivative is undefined. Okay. at x equals a. All right? The equation of the tangent line, and they go right out and say it here. And we actually have a name for this. It's capital L of x. Remember, I keep telling y'all that the case of the letters matters. You're going to find out more and more why I keep saying that. L of x equals, and then I want you to tell me, I'm going to write this in a slightly different order than the book does in case your book's open and if you look back at it later. But I want you to tell me when we get done what all this means and how this relates to what we've been doing the entire year thus far. All right, so f prime of a times x minus a plus f of a. Wow, you have a lot to say. Nothing? You got nothing? Really? You really don't have anything, because I'm like questioning you. You're cutting your eyes. I'm like, please don't ask me that. Okay, well, let's write it another way underneath it before I say anything at all. So what have I done when I write it as L of x minus f of a equals f prime of a times x minus a? That's point slope form, right? Okay, so tell me about the little pieces of what you see in front of you. Right, f of a is the y when a is x, right? Okay, and what's f prime of a? The slope at a. And the definition here just told you this is a tangent line. That's why I did not think I'd have to like point that out to you or rewrite it in some way. Now, so we've got a new name for y in our tangent line, L of x. What's the significance of that? That reminds me that I am linearizing the function. What does that really mean? That means that I'm treating the function everywhere that I'm dealing with it as if it's a line. Why is that easier? Because it's a line, right? Okay. It's also easier for processors, as in computer chips and whatnot. Why? Because when you have to run a computer chip in a piece of machine for a span of time, you want to make the work on it the lightest that you can. Not only the fact that if you can simplify computations that chip is processing, then you've shortened the time that it has to spend on it. So you've diminished the difficulty, complexity, which also limits your time that you have to spend on it. Does that make sense? So if I'm writing a program, if I could write it so that it always used a tangent line instead of some crazy function like some of what we've been dealing with lately, then it would be a great improvement, right? So that's what that's for. All right. And this is obviously, and I'm not going to write this phrase unless you need me to, but based on what just happened, I'm not sure whether we need to write it. Where is this good for?
For any room
Wherever x equals a, right? Because just because I can do the linearization of a function at some point doesn't mean I can do it at every point, right? But wherever the function is differentiable, right? Does that make sense? Okay, so keep that straight. So we won't write that down in spite of the stilted response I got. Now, I want you to write this underneath it, but I'm going to go to a new screen just for more room. Up, undo that. And this is still sort of part of the definition. There's some embedded terms and whatnot. So what we've learned from this, what do tangent lines tell us before I go any further? It tells me about the behavior at that point, right? And where does it lose validity? The further away from the point I move, the less valid that approximation is. Doesn't that make sense? Has everybody got a picture in your head? What should happen when we're talking about tangent lines now, we've done it so much, is that you should see a tangent line attached to a function, and you should be able to see that no matter which way that function is going, whether it's concave up, concave down, increasing, decreasing, it doesn't matter. That line is only going to be perfect at the point, and it's going to be really close as long as I'm really close to that point, right? And what constitutes really close? It depends on what you're doing. Does that make sense? Okay. So basically what we've discovered in this new notation as calling our tangent line capital L of x is that this is approximately f of x. So it's an approximation. Does that make sense? Okay? And we've known that all along, right? And this is the standard linear approximation, but I don't think we necessarily need to write that down. Okay?
But if that's the tangent line, wouldn't that? Because wouldn't that be?
You sure?
Because the L of x is the tangent line, right?
Right.
So if the tangent line is on the function, how is it?
It isn't. Okay, rewind to what I said right before I wrote this. What do we use tangent lines for?
To determine what points.
Right, it approximates the function value and behavior on some interval, right? How well does it do it? Okay, let me rewind. Marquise, where does my tangent line tell me all those things about my function perfectly? At that point, right? And then what happens as I move away from that point in either direction? It doesn't work as well, right? The further out I move in either direction in general, the less accurate it's going to be. Does that make sense? So it's an approximation. That's just like if I said, okay, approximate, and I gave you some value. What would dictate how hard you tried to get a really, really good guess? What you're doing with the approximation, right? So in the same way here, I know that my tangent line is perfect at the point of tangency. It's going to be less perfect the further away I move. Has everybody got that straight? Okay, so all that being said, and Marquise and I having that little conversation there should help you answer this. If you had to guess, where is the center of this process? At the point of tangency, right? Okay, the center of the approximation, and believe it or not, the only part of that's technically the term here is the word center, but put in parentheses there, of the approximation is the point of tangency. All right, I think I want to jump over and do an example with you before we go further here. So let's look at number 2. And I'll go to a new screen just to make sure I have plenty of room to write here. So as our example, and you don't have to have your book open, I'll write it up here. Your function is f of x equals the square root of x squared plus 9. And a equals -4. The directions here tell us to A, find the linearization L of x of f of x at x equals a, and B asks how accurate is the approximation, and we're not going to, well, we'll go ahead and do that, and then we'll come back to the other discussion, okay? All right, so part A, if I want to find L of x, what is this a new way of asking me to do? Find the tangent line. So I got to have the derivative if I'm going to find my tangent line, right? So if I'm going to do that, I want to think of my function how? Right, in derivative-friendly form, but specifically, what would that be for this one? X squared plus 9, the quantity to the 1/2, yes? And some of you don't tend to write that, but I'll leave that to you as to how that affects your accuracy of your answer. So my f prime of x is going to be, this is where y'all do the work that you know how to do, okay? 1/2. Wait, to the what? -1/2 times 2x. And what did we just apply? The chain rule, good. All right, so this is equal to,
X over,
why is it x over?
because the 2 and the 1/2 cancel.
Okay, so we need to show that in the previous step, not just drop them, okay? Because that indicates I didn't just not write this. I knew this was my answer. Does that make sense? Okay, so tell me again, x over what? The square root of x squared plus 9. Okay, now, what do we need to know about or why do we need this derivative? Find the slope at the point, right? Because I'm using this for a linearization. Okay, now, your instinct by now is probably to do what when you find a derivative? Make a dangram, find the second derivative, figure out where, and for the dangram, what do I have to have? Where the function would be undefined or 0. At a glance, you should be able to tell me the answer to both of those. But we don't need it here, but just for practice, where is this undefined? Never. What does the graph of x squared look like? Okay, you don't need to tell me that, but you know what the graph of x squared looks like, right? Well, what happens when I add 9 to x squared? What does that graph look like? Slides up. Never 0. Right? If you want to think of it graphically. All right, if you think about it from the perspective that x squared at the smallest is what? 0 plus 9 is defined, right? Okay. And it doesn't matter if I plug in negatives or positives, 0 is my smallest possible answer. This can never be negative. The only way this could ever be, 0. The only way this could ever be 0 is if x squared could somehow be negative 9, right? You want to get to a point where you're thinking that as you look at these, okay? So never undefined, and 0 is 0. Okay. So, but we didn't care about that. That was just practice. So what do I do with my derivative? We're going to plug in our negative 4. So I want f prime of negative 4. So I'm writing my left side, boys. And I'm saying boys because I don't think I have any females who are still leaving off the left side. When I say left side question mark, this is what I'm talking about. You only need to write it once. You just need to tell the world what it is you're about to do. Yes, Becca?
Here, do you not have to do the little thing that we did whenever we were doing implicit differential? Remember where you do the bar,
and like x equals negative 4.
and then x?
Nope. In fact, this notation is what you want to use unless you have to use that. And the only time you have to use that is when, let's rewind to implicit, because this is good embedded review. What is implicit differentiation?
X and Y cohabitated with implicit.
That's right. X and Y cohabitating. In other words, my derivative typically has both x's and y's in it, right? So it'd be clunky notation. Some context, and maybe this is old school, but what we used to do is when that happened, you could also write f prime and then put a point in your, like in coordinate form inside your function. So I haven't seen that as much in recent textbooks, so maybe the math world is getting away from that while I'm hiding in my room. But this is your favorite method, right, of notation? It's less to write. Don't use the clunky unless you have to, okay? And when you use it all the time, you make people scratch their heads. And then they get dandruff on your test. Just had to throw that in there. I'm sorry. I'm delirious. Okay, so what do we have on top? Negative 4. And on the bottom, we have, what do I get when I plug in negative 4 into x squared? Plus 9 is 25. So this is negative 4/5. And you don't have to write every step, but you want to write enough that the world knows what you're doing. And technically, you could go straight to the negative 4/5, but just do it with care, because when you start doing things without steps, you start making mistakes. All right, so what else do I have to write my line? I need my x and my y. So let's come back up here to the original function line where we first wrote the problem, and let's write that as a point. Obviously, we have negative 4, but the cool thing is we really just got it, didn't we? That is the y-coordinate, because it's the denominator of my... I wish my videos could record my facial expressions when moments like that, just for moments like that. This was a Hollywood production, they would have to include that because, oh Lord have mercy, help me. All right, so instead of y, what am I going to put?
LX.
Oh, sweet Jesus. Capital L of x. L of x not L of x equals L of x. Well, we can, but if you're comfortable, you can go straight to the equals form. But it might be helpful if you could do L of x minus 5 equals negative 4/5 x plus 4. Yes? So in true function notation, and since you're writing, anytime you write something of x, you are using function notation. And so that should remind you that that is always, function notation requires that that term be by itself. Does that make sense? Okay, so this is equal to negative 4/5 times x plus 4 plus 5. Simple enough?
So we don't have to like simplify that?
No. You don't have to simplify that any more than you had to simplify point slope. As long as you isolate the function notation version of it, you're good. Because otherwise you just look like you don't really get functions in the whole concept. Yes?
How can we get the 5 on the left side of the equal sign first?
Someone answer that for me.
Point slope.
Yeah, because I have drilled into most of y'all's heads by this point that point slope form is the way to go. And that when you're just writing a tangent line, point slope is still fine. When you're doing a linearization, that's telling you to use the function notation L of x. And so you're going to have it by itself. If you're okay with doing that all in one step, that's fine. But for most students, having that intermediate step is going to help you think about it. That's the only reason I did it. All right. Now, B says, and we're going to go ahead and do this even though we haven't finished the lesson discussion, but I'll get back to that in just a second. The directions for B tell us to, or actually it's a question, how accurate is the approximation, and I will write this out from the directions, L of A plus 0.01, I'm sorry, 0.1, I lied. It could just as easily have been the other. Is approximately f of a plus 0.1. Why do you think they have this written this way in the directions? What's the significance of what you just wrote? What does that remind you?
That was to remind you that like L of x is like y.
You, before you get to college, your goal in the next 6 months is to stop saying like. I don't think you can make a sentence without it. Have y'all ever heard her make a sentence without the word like in it somewhere? No. Okay. Because in math and science classes, you don't want to be using the word like, because math and science professors are going to do you mean like it, or do you mean actually it? Right? I mean, because Valley Girl talk, I mean, that is so like pretty. Really? Is it pretty or is it not pretty? Can you make a statement? What is your deal? Okay, so let's try this again. What does this remind us of that we just talked about this morning? Thank you. L of x is the approximator of the function. Why are we making it a line? Why are we trying to turn it into a line?
Because lines are easy.
Because lines are easy. Does that not make sense? Okay, so they write it this way in the directions to remind you. Well, in our case, what is our L of A? Or what is A? Negative 4. So for our problem, it's going to be L of negative 4 plus 0.1. And no, this is not a no calculator question. And I just put my parenthesis without the 1. Okay? And this is stupid simple. Okay? So when you're in the first part of the assignment, don't second guess yourself. It's just this simple. Okay, well, if I ask you to approximate something, and then you approximate it, and then I ask you how accurate was your approximation, how could you figure that out if you haven't already?
Use your calculator and graph it.
That is all about the graphing.
Can you repeat that question again?
Okay, if I had you approximate something, and then you gave me an answer, okay, you said, okay, my approximation was 7. And then I'm going to ask you, okay, so how accurate was your approximation? I have to compare it to what? The actual function value. Doesn't that make sense? Okay, that's all you're going to do here. Okay, so the first thing I need is my L of whatever negative 4.1 is. So now I'm actually going to put an equal sign, because the first thing I'm going to do is figure out what negative 4 plus 0.1 is. Negative 3.9. Everyone concur? That's good, because that's what it is. All right? And then I'm going to put another equal, and I don't know why I'm writing so big. I do know why I wasn't zoomed in. Equals, I don't mean the answer. Tell me what to write to show where my answer is coming from. Negative 4/5, parentheses,
Negative 3.9 plus 4.
negative 3.9 plus 4. Okay? Plus 5 outside the parentheses, right? What did the people who were actually talking, which should have been like 20 of you, and it was maybe 3 of you.
I just took the
We just wrote an equation of the line. We're plugging a number into it. This is algebra 1, if not pre-algebra that we're doing right now. So y'all need to quit looking so scared. I told you this was easy. So what do we do now? All right, if I had to do this without a calculator, I could, couldn't I? Because negative 3.9 plus 4 is, aka 1/10. And then I have plus 5. All right, what is negative 4/5 times 1/10? Negative 4/50. Now, we don't actually have to do this for this problem, and I'm not suggesting y'all should do this on all your homework problems, but you've got to start practicing not using a calculator for things that you don't need it for. Why? Because half your exam will be without a calculator. Okay? All right, so then we're going to change 5 to 50ths. So if I need a 50 on the bottom, that's basically doing what to that 5? Multiplying the top and the bottom by 50? Duh. I don't know what just happened. Sorry. By... Sorry, I got sidetracked in my technology up here. Yes? Is that simple? What's 5 times 50? 250. So my answer is 246 over 50. Now, it's pretty well stuffed. All right. Yes, we would reduce that, except for the fact I don't really need to, because what was the original question? How accurate is it? And we can go ahead and turn that into a decimal.
We say it's almost 5.
Because if we, okay, it is almost 5, isn't it? But we want to know how accurate it is. So somebody tell me what this is as a decimal.
4.92.
Mackie just said it's 4.92. Surely you have a calculator, since I said from the beginning you're going to need a calculator to do this, and literally like 2 people touched their calculators when I said that. Oh my gosh. This is not okay. It's aggravating.
4.9.
Almost as aggravating as the stupid woman driving down 97 at 55 miles an hour this morning with her park lights on. I wanted to stop and say, you aren't smart enough to drive. Go home.
4.9.
Walk. I'll get somebody to tow your SUV. 4 point what?
92. Did you guess that?
No, it's in my mind. I don't have a calculator.
Is it actually 4.92?
Yes, it is.
We could have said 46 times 2 is 92.
Okay, so we got 4.92. What's the actual function value here?
4.92
Okay, so f of, and how did you get that, Morgan? She asked her calculator for f of negative 3.9. And let me just give you a little hint here. F of negative 3.9. Let me show you how smart this is, okay? If you will go to your calculators right now, in your first available input line in your graph, type in the function. I will pause while you do that.
Wait, the one we just...
The function. Yeah, we're on this one problem. And keep a mental note of where in your calculator you're typing this. As in F1, F2, F7, F3, whatever. If you have an Inspire. And if you don't, pay attention to the Y of whatever. Y1, Y2, whatever. All right, Inspire people. Now, go to your main screen. Because here, this is what you should be doing to check yourself. And I haven't mentioned this before. Some of you may have already found it, which might explain a lot of homework I've collected with no work on it. But if you go to Menu in your main screen, Menu, Calculus, Tangent Line. All right, now it's going to ask you for the function first. So type whatever you just, wherever you type that. So if you did f2 of x, type that as f2 of x, comma x. What's wrong, Marquise?
Okay, you say, okay, I got a question. Do I have my tape?
Where did you put your tangent line? Or where did you get your tangent line?
I want the menu calculus and tangent line, then I put that equation.
Okay. How did you get your tangent line?
Off of
I was talking you through the steps. I'm just wondering if you decided to do it your own way instead of listening to what I was telling you. The whole point of graphing it first on these, where you know you're going to want to know, like, all kinds of details about the function, it's helpful when you have your calculator to graph it, and y'all need to get in this habit because this is such a time saver. Instead of typing the function every time, where you've just graphed it is how you're going to tell the calculator which function to use. Do you see what I'm saying? All right, so if yours was in f2 of x, then you would have tangent line, and the first thing you have to do is tell it what function you're working with, so just type f2 of x. And what should happen is it should be bold on your screen. And then after that, put comma, x, enter. You get a tangent line, yes?
No, it's just too few. Okay.
No, then you put x equals -4.
I didn't really want the -4 there. It should be able to get, well, I guess it wouldn't do the, okay. So then tell it -4. So after the after x, put comma -4.
After we graph how do we get to the?
You go to the calculate screen.
You put x equals -4.
And then menu, calculus, tangent line. And then for your function, you're going to type f whatever of x, depending on where yours was, comma x, comma -4, enter.
You put comma x equals -4.
You have to say x equals -4?
Yeah.
I didn't remember that particular syntax. And if you ever don't know the syntax, if you go to the little book
Or
button,
you can do it
when
either way.
when you pull it up in the catalog, it'll show you what the syntax is.
Miss Sweetie, you can do like equals -4 or comma -4. It works to like comma x, comma -4.
Yeah, that's-
You can do comma x equals -4. You can
Okay.
have to say that.
Yeah. I thought I remember doing it that way. So, okay, are we there? Marquise, why are you standing up? Why do you have two calculators in your hand? You probably can't because you're in press to test mode. So turn your calculator off and sit down. You need to deal with that on your time. This was what, Thursday or Friday we were talking about your calculator being in that mode? And I told you I didn't have time to deal with it that day, but I'll fix it if you'll let me.
No, I was trying to figure out how to.
So that we'll be able to have something to post here. Differentials. Now, when I asked you to speculate as to the content or anything about this lesson based on its title, most people focused on the word linearization, but Becca very quickly went to the word differentials. Maybe it was the last word she wrote that made her think about that, but those are two words you should be very comfortable with, right? Or at least some form of them. All right, so differentials is related to the derivative. All right, tell me in the fractional definition of the derivative. What is it? How would I write that? How could I write f prime? dy dx, right? Okay, here we go. So let f of x equal y. And what has to happen for it to have a derivative? What's the word for that? Differentiable. And when I say let it be differentiable, I mean everywhere. Okay, so if you want to write everywhere, you can. The differential and let me see if I can help you think about this, because you know, if you've gotten nothing else out of being a student of mine since last year, you should understand that one of my primary goals is to get you to think. Okay? And at some point I have some quotes I want to read to you about why that matters. All right, but what is the root word of differential? Different. Different, which kind of relates to what we just did. How far is it off by? Does that make sense? Okay, so the differential dx, and that is a term, is an independent variable. Why does that not surprise you?
It actually can change it.
What was that? Mackie, say that louder, please.
So, x star
it is the independent variable, right? By definition, you should have learned that in Algebra 1. Is an independent variable. Now, the reason it's independent is that, okay, what was our differential in what we just did on that part B on that last one?
0.0.
0.1, right? Where did that 0.1 come from? It was arbitrary, right? It was given to me. Okay? So if you're an engineer and they said, what's our differential at 2 centimeters away? Well, then they've just supplied for you the specific location, right? So that's independent in the sense that that has nothing to do with the function. Does that make sense? It's just what somebody wanted to know. All right? So what do you think? So we're going to say, and the differential. What's the other one? There you go. The differential dy, again, that is another term, is a dependent variable. So in other words, now, I'm a brave woman. I also don't mind taking risk, which I guess is sort of the same thing. So I'm going to ask a question. Can anybody connect this technical talk to something we've been talking about already today? Okay, I heard one little stammer, and then I'm going to let Clark have the floor, but I'm going to give you a hint. How did we already know about these two variables to some extent? dy dx, right? Okay, what is the derivative? Slope. What is slope? The change in y over the change in x. What's dy? The change in y. But now, what is this change referring to here? In the context of tangent lines and functions.
The change in accuracy.
Let's just say I have this curve f. All right? And I compute the tangent line L of x. We should have a good idea of what that picture should look like, shouldn't we? Okay. Let me rewind your question. Or Clark, do you want to go ahead and say what you were going to say before? No? Okay. All right. I didn't want to steal your thunder here. All right. But what did we say already this morning? And we've talked about pretty much throughout the year since I very first taught you how to write equations of tangent lines. What's going to determine the accuracy of this linear approximation? How close I am to the center of the approximation, right? So if I'm really close to the center, as in on it, how close is it going to be? Exact. If I take a tiny step in either direction, am I going to get the exact answer? But I'm going to be close, right? Okay? So that's what this statement relates to. Tell me how it relates to it, because what is dx? What does dx tell me about where I am relative to the center? How far away and in which direction, right? Because if it's negative, it's going to be to the left of it. If it's positive, it's going to be to the right of it, being the center. Does that make sense? Okay, how about the dy? What does that tell me? Does it tell, okay, now dy in the dy dx does tell me the change in y, right? Okay, but specifically in the context of using your linearization as an approximation of the function, what do you think dy is going to tell you? How far off I am from the actual value. In the same way that the dx tells me how far I am from the center, the dy is going to tell me how far I am from the function value at that point. Does that make sense? So the dx is going to tell me the distance on my in x, in terms of x, just horizontally, how far away from the center I am. The dy is going to tell me how the distance between my tangent line at that point and the function. Does that make sense? Okay, so when you look back at the B that we just did, how good was our dy? That's pretty impressive, wasn't it? Do you see what I'm saying? Wow. I hope that wasn't fake. Amy?
No, that makes this, the first equation that we wrote make a lot more sense.
Good, good. And it should also connect, and that's why I did it where I jumped in and did number 2 with you, so you'd see the mechanics of it are stupid simple. The interpretation is the hard part, okay? All right, the only other thing, in fact, let me do, I was debating about whether or not I want to show you this, but I guess I will. All right, so if I have, this gets into such a conversation. All right, so another way to write f prime of x is what? dy dx? Okay. So we're going to put our f prime on top, or well, dy dx. So if I specifically want to know what dy is, how would I write that?
Multiply by dx.
Technically, you're multiplying by dx. So what you end up with is dy equals f prime of x
Times dx.
dx. Does that make sense? So if I wrote, and I didn't emphasize this notation, that's why I'm kind of hesitating here. All right, what would df mean? What would that relate to in what we've just done? The dy. Because remember, the function is y. You know how I've said that since last year? The function is y. What is x? Yeah, that's just where it happens, right? It's the location. The what is the function. Does that make sense? All right. So we could also write df equals f prime of x dx. So let's just say that we had f of x equals, we'll put a little asterisk here, so this is sort of an example in detail for you to see what it is. All right, f of x equals something simple. Let's say 7x squared plus 4x. That's a plus. It doesn't look like one. Let me fix that. Well, I thought I had the eraser. So then what would our f prime of x be? 14x plus 4. All right, don't factor it. Resist the urge. Just be happy that the urge was there. And for those of you that it wasn't, where have you been? All right, so then my df would be, based on what we just said.
14x plus 4.
So we want to put that in parentheses because that's one thing we're replacing, right? So 14x plus 4, close parentheses. What else do I need? dx. Okay, so it's kind of like we're zooming in terms of our notation on that concept.
So, did you
What do
find,
you use that for?
Go ahead, Marquise. Morgan didn't realize you were talking.
Oh,
would you like take two separate values of x, or would you find what x is, but forget your dx? Like, find a change in x.
Well, no, like on that first part, I want you to do exactly what we did. Just to remind yourself, the error is just the difference between my answer and the original. I just need to be able to tell whether it was an up or down differential, right? I mean, difference there. Does that make sense?
Yeah.
Okay. Morgan, what were you going to ask?
I get it, but like I'm just not quite sure. Like that last part you just wrote. Like, what would I use that for?
Stay tuned.
Okay.
You may or may not get your answer today, but there will come a day where you're like, ah. And I want that. I don't want to take that from you. I want you to be able to have that happen. All right, differential estimate of change. I'm going to jump out on a limb here. I'm going to put ellipses. And I want you to use the approximate sign, and I know this is bad grammar, but we're going to use it just to speed us up. The approximate change in f, which is really what? Y. When x changes, that's not exchanges, x space changes from A, and there's going to be a dramatic pause, and I want someone to go, oh, from A to A plus dx.
So it was
You're changing x.
point one or dx in the last two.
That's right. So 0.1 was our dx in that last one, right? So if I was at -4, 0.1 says go in which direction? To the right, because it's positive, right? So from -4 to 0.1, I wound up at -3.9. Not rocket science, guys. That's what, 6th grade? All right, you with me? Okay. So when I go from A, which is what relative to this whole conversation, big picture? The x coordinate at the center. Yes? At our point of tangency. Does that make sense? So A plus dx means I've left the tangent line, the point of tangency, and I've moved away. So what's probably going to happen? It's going to be approximating. How well is it going to approximate? Depends on, right, how big dx is, right? So if I made dx 700, probably going to tell me absolutely nothing, right? You see what I'm saying? Okay, here we go. So here we go. df equals, and really the immediate reason for everything I just did prior to that in your notes should be obvious here, equals f prime at a, what does that mean? So my derivative at a, in other words, I'm going to plug my a into the derivative and get a number, yes? Times dx. Now, you don't have to put, I'm putting the dot there to remind you that when it says f prime of a dx, that's a multiplier, okay? Now, this is hideous, and it's a pain in the butt to write out, but it's a very required, and I say very required because it's tested, and this is Newton's method. Why do you think it's called Newton's method?
I think you said Newton.
Mutants? You thought mutants like Ninja Turtles?
I think you said Newton.
No, Newtons like fig. Newton's method. I love that movie. Oh, I saw a sweatshirt, I think it was in Kohl's, in the men's department no less, and it was the Ninja Turtles, all 4 of them wearing Santa hats and grinning. I'm like, that makes it a Christmas shirt? Okay, all right, Newton's method. All right, so it's named Newton method because Newton came up with it, Sir Isaac. Number 1 in this process, and this isn't really the method. The equation is actually the method, but it's the process you're going to go through. So you're going to guess a first approximation. To f of x equals 0. Now, a couple hours ago, if you'd asked me how quickly I expect a response to the next question, I would have said, oh, like a millisecond. But after this morning, I'm just going to count to 10 before I react, okay? Big deep breath. Speaking graphically, what is the significance of f of x equals 0? Thank you. It's where f of x crosses the x-axis, yes? Now, listen to me carefully here, because if you do what I'm just about to tell you not to do, you're not going to know anything in this lesson. And this lesson's too easy to understand if you just do what you're supposed to do. You have to go through the tedious parts of it to get it, okay? All right. So if we're going to guess an approximation, and I can use my calculator, when you're supposed to find f of x equals 0 and you graph a function and you look at it and it has like 3, let's say it has 3 x-intercepts, aka 3 zeros, right? What do you hope happens when you hit the enter button for the graph?
That they're just whole numbers.
Yeah, that their whole numbers are, at least they're integers, right? And so they show up on the little tick marks on your graph, right? But so when would they be something you don't know exactly? Okay, how does that show up in the graph on your calculator? When I'm between the tick marks, right? Okay, so here's what should happen. If I'm between, say, 4 and 5, what would be a decent guess just to get me in there? 4.5. So that might be your first guess. If you use your calculator to find that 0, you've defeated the purpose of this process. Don't do that. So don't use your technology other than just to graph it when you're left to pick your own approximation. A lot of times they'll give you as a first approximation, okay? So get that straight. All right, so that's your first step. And then it says in your book, and you will see this when you're in your book later, and I'm not going to have you write this, a graph might help. No kidding. Where else was I going to get my approximation? All right, step 2. Use the first to get the second. Second to get the third. What would the next thing I write, if I were going to write it, be?
Third.
And put ellipses after that. Because you follow that pattern. Now, how do you do that? This is where Newton's method actually comes in. This is a process, okay? So here's the actual Newton's method, is what I'm about to write. Now, I'm going to take a big deep breath again, but I'm going to ask if you know what this means. X sub n plus 1.
Whatever you guys
Just the value of x.
We've done something
With
more.
polynomials. Yeah.
Was it in that packet, there was like x n plus 1, and then like x n plus 2, and then it had like a dot dot dot, and then it like kept going, and then there was like,
And I really just.
Oh yeah, it was in our lesson functions.
it was in a packet, I remember.
Let's just keep going. We'll come back to this. All right, x sub n plus 1. And if I write this, maybe this will get you going.
I think I got the answer. Okay, that's like, okay, we got x plus 4, and then it's like our second x that would be like, when you plug.
I'm not getting that you understand this, but I'm going to write something and then I'm going to pause. This is not the whole thing, so I'm going to write x sub n. What is the relationship? This is a better question that you should be able to get. What is the relationship between x sub n plus 1 and x sub n? You said an extra one? It's one more. It's the next one after, right? That subscript notation means this is the one that follows the one before it. X sub n is the one before it. Does that make sense? Okay? So minus, and this is the weird part because you always want it to be plus, but it's minus. The numerator of this is f of x sub n. So what does that mean I'm going to do? Whatever x sub n is, I'm going to plug it into the function I'm working with, right? And then in the denominator is f prime of x sub n. What does that mean? So in order to use Newton's method, what 2 pieces of information do I have to have? Well, actually 3. Well, let's assume we aren't given the third one. So obviously from this equation, what do I have to have? I have to have an f and its derivative, right? Okay? And then the x sub n is your initial guess. But this is what's called an iterative process. That means you do it over and over again. Okay? And then the directions will typically say until you are at 3 places of accuracy or something like that. And let's just do an example real quick, and then we're done. All right, so here's our example. Let's do f of x equals, and in the interest of time, I'm going to use the one in the book just so I don't make one up that's harder than it should be. All right, x cubed plus 3x plus 1. Okay, before I found, okay, let's go in the order of the process. What does step 1 tell me I need? I need a guess, okay? So what am I looking for on my graph? So that means I'm interested first in where f of x equals 0. But don't use your technology, just glance at it and somebody get me a number. And what you're going to write on your paper is x sub n. We'll call it x sub n, but then I'm going to come back at the end and ask you what we could have called it.
I think it would be -1.2 and 0.
Between -2 and 0? Well, what, I mean, look, you tell me. Now, if you're going all the way between 0 and -2, you want to be close, but you don't want to be exact here. The closer you are, the less steps Newton takes. So it's close to the -2? That's what I wanted to know. Okay. So -1.7, she says. From looking at the graph.
No, I think it was,
You disagree?
Yeah.
Well, speak.
I wanna say -0.7.
Negative 0.7 or 0.4, because it doesn't
Yeah,
pass
it's
through.
not, it's between 0 and 1.
It's between 0
I
and
mean, 0 and -1.
Never mind.
So negative what? Give me a guess. Point.
4.3. No, it's 0.4.
I'm gonna split the difference between your two guesses. We're gonna say -0.5. Okay?
Wait, how would we approximate without a calculator?
You won't.
You don't?
If you're without a calculator, you will be given. A lot of the problems will say using -2.4 as your first guess. Use Newton's method to approximate the function value at -3. Okay? All right, so that's our first guess. So then if it's our first guess, what should I use instead of x sub n? And I'm going to leave this in a little cloud up here. X sub 1, because it's my first guess of what x could be, right? Oh wait, but on the left side, what is the formula? Because I want y'all to tell me, because you'll be able to use it better. So if I call that, so put a little error here and write this is x sub 1. And the reason I'm calling it x sub n is for the formula directly. Does that make sense? Okay, so on the left sid, I'm going to be finding what? X sub 2. Because it starts from x sub 1. How did the formula tell me that?
Because it's
N plus 1 and n as my subscripts, right? So this is my second guess based on my first guess. And that's what that second step in the process tells you. All right? So I'm going to start with my x sub 1, which was -0.5. Minus, and this step, for this term, I definitely need my derivative. So I'm going to hop over here, and we're going to do our derivative. F prime of x equals 3x squared plus 3, right? So I need f prime of -1/2. Do that with your calculators. And you want to stay in decimals here. I know that's really counter to what I normally tell you, but in Newton's method, you're going to stay in decimals. And pretty much this whole lesson is decimal based. 3.75. Or no, that's my derivative, right? So that goes in the denominator. I also need what? In the function. And when you're doing Newton's method, this is where it would be really helpful if you've defined it over using your graph. Using that trick I showed you a few minutes ago. Because this lesson gets really tedious if you're having to write out, type in over and over and over again.
2.625.
Positive?
Yes, ma'am.
2.625. Don't put your calculator down because you got to tell me what that is. And these answers you want to have like probably 5 or 6 decimal places. 0.7?
Oh, wait.
You gotta
Negative,
subtract those
like
negative
negative
0.5.
0.5.
Oh, I thought you were giving me. I was gonna say, is that 0.7? So what's my result?
Negative 1.2.
Negative 1.2.
Yes, ma'am.
Negative 1.2 is the whole thing, right? Okay. Well, that is my second guess. So now, what would I write on my next line? X sub 3 equals negative 1.2 minus. Now, what do I have to have? Right. Do you see why you're going to want to have that little system I showed you a while ago? And if you weren't paying attention, Sucks for you. And Marquise, if you will leave your calculator with me, I will get it out of press to test mode. You can come back and get it after second block.
Does it tell you like how many approximations
Yeah.
to go?
Yeah, the directions will tell you. I just wanted, we're just gonna do this so you get the rhythm of how it works.
Do you want answer?
What goes in the top?
Negative 4.37.
So what's that gonna, well, I'll write it that way. Negative what?
4.328.
328 over 7.32, which gives me, and these are approximations here, because you're gonna do some kind of rounding on most of them.
Negative 5.591.
Negative
Point
591?
257, but 591.
257?
Yes, ma'am.
Okay, we'll take 6 places there. Then my x sub 4 is the negative 0.591257.
Wait, that's
Wait, no, no,
what
no.
it is before you.
Sorry.
Yeah.
I'm sorry.
Wow, that took way too long. It shouldn't be Mary Lindsay like running me through this. Y'all should all be talking to me.
It's
Negative 0.60873.
608 473
743.
743. Okay, and then that's my
What are
number.
you trying to get this number to, Sierra?
No, you're trying to get it to be as accurate as it can. Do the 2 answers we've gotten so far look anything alike? What will happen is the further down you go, the numbers will start. You'll start to get the same first decimal, and then the same second decimal, and then the same. Because what happens is you zoom in on it, basically. Okay, so let's do this one. So, and the problem will typically tell you how many decimal places of accuracy you have to have before you stop. And this is why getting as close as you can to a good approximation without using your technology will help you. Okay, so minus. So what do I have to have
0.337285.
on the top?
Yes, ma'am.
Negative point,
337285.
and on the bottom?
$7.8883.
Wait, for the derivative?
Yeah.
I got 4.11.
Yeah, me too.
That's why everybody needs to be doing it. Especially with this many decimals, you're liable to have a keystroke error. 4 what?
1117.
4 point?
Yes, ma'am.
3 ones?
Yes, ma'am.
And a 7.
What did you put in for your?
It's all, I got negative
Yeah.
one.
Never mind. Never mind.
I got negative
Mary Lizzie just resigned.
1.05.
What's the top?
Negative 1.
See, there's like 8 people have that answer, and you're all just letting Mary Lizzie just yell out numbers, and I'm writing whatever the first person I hear says. You've got to be on it better than that. What does that give you?
Negative 0.352934.
I'm going to put a footnote here to this so we can close out our notes. See example 13 for the finish line. And I just wanted you to see how you use it. Example 13. Whew, that's a lot of examples. Example 13, page 245 to close that out. Work day tomorrow. Have a fabulous Monday.